Oscillations. Let's consider small oscillations near the equilibrium. The force is given by negative derivative of the potential energy with respect to coordinate q. And the force itself could be a restoring force, which is given as a displacement raised perhaps to some power. We can always expand the potential energy near the equilibrium point, Q naught. Using Taylor expansion, we write U of Q as U at Q naught plus the first derivative of U evaluated at Q naught times the displacement Q minus Q naught plus half of second derivative of U at Q naught times Q minus Q naught raised to second power plus higher order terms. We know that at the equilibrium the first derivative vanishes, so we can write potential energy at Q minus potential energy at Q naught to be given by half of coefficient K times Q minus Q naught squared, where K is simply the second derivative of U evaluated at Q naught. Likewise, for kinetic energy, generally we can write that we expect it to be of the form where Q dot squared comes in times some coefficient, which generally can depend on the coordinate Q. We can evaluate that approximately to be given by half of A of Q naught times the velocity Q dot squared. That's what we get approximately near the equilibrium. This allowing of the coefficient in front of Q dot squared to depend on Q is the most general form of kinetic energy. Now, if Q is a Cartesian coordinate, we know that this coefficient A of Q is simply mass. Knowing potential and kinetic energies, we can write equation of motion from which we will find that for small displacements delta Q, defined as Q minus Q naught from the equilibrium, we will find that the angular frequency of these oscillations will be given by coefficient K divided by this coefficient A, mass equivalent, and it's going to be constant. In other words, not dependent on the amplitude of oscillations. So the quadratic term of the potential, which approximates the potential energy well near the equilibrium, in fact describes simple harmonic oscillator. On the other hand, if delta Q becomes large, and at the moment we are not defining what large and small is, we will see that the frequency of the oscillation will become amplitude dependent. Whenever we have such amplitude dependent frequency, we call such oscillations unharmonic. So, for example, back to our diagram, as the amplitude of oscillation increases, we will see that the frequency becomes dependent on the amplitude of these oscillations. General form of solution for simple harmonic oscillator we will write in complex notation. delta Q will be given by real part of complex valued constant A times E omega t, where complex A is given as amplitude times e raised to power of minus I delta. Capital A is amplitude of the oscillations, and delta is the phase determined by the initial conditions. We mentioned previously that phase space trajectories of oscillations are elliptical. In other words, coordinate delta q and momentum that corresponds to delta q, oscillations will lie on the elliptical orbit and will be moving clockwise with the area of this ellipse increasing with increasing energy. The energy itself will be proportional to the amplitude of the oscillation square. Note that the phase space trajectories cannot cross. This is true for phase space trajectories in general, not just oscillations. It's easy to see that if trajectories in phase space could cross, then it becomes ambiguous which trajectory to take after the crossing. For example, you could imagine trajectory going like this, or trajectory going like this. Since the solution to the equation of motion is unique, we cannot allow that to be the case. However, even though phase space trajectory cannot cross, they can come very close to each other. In other words, you could imagine a scenario in which these two trajectories and these two trajectories in fact nearly touch each other, almost crossing. Finally, the trajectory can cross in a lower dimension or projected phase space. In other words, if you take a projection of a higher dimensionality phase space to a lower dimension phase space, their trajectories can cross.